In the last video, we saw how heat is transferred between a hot object and cold object. In this video, we'll see how heat is involved in chemical reactions and how heat can be used to heat up or cool down things. On a hot day, a rock and gold cup lie in the middle of a parking lot. Which object contains more heat? Stop the video and think about it. The answer is neither. We define heat as the energy transferred between two objects due to a difference in temperature. Objects do not contain heat. Heat is transferred between two objects. Internal energy and enthalpy are the two types of energy that an object contains. When this substance comes in contact with something at a different temperature, some of the internal energy is converted into heat. That amount of internal energy is called enthalpy. So remember this equation. Also remember that delta anything means final minus initial. So if delta H is greater than 0, that object has more enthalpy than before. In this endothermic process, heat was absorbed or supplied to the object. Stop the video and explain to yourself delta H less than 0. And the answer is an object has less enthalpy than before. In this exothermic process, an object releases or gives off heat. We know heat is the energy transferred between two objects due to a difference in temperature. We know temperature is the average kinetic energy of a substance. It tells us how fast or slow the atoms and substances are moving. Internal energy is the energy inside atoms and molecules. A hot object has a higher internal energy than a cold object. So when a hot object comes in contact with a cold object, those fast atoms in the hot object collide with the slow atoms in the cold object. The fast atoms transfer energy to the slow atoms. That energy transferred is called heat. The fast atoms move slower, which lowers the temperature of the hot object. The slow atoms move faster, which raises the temperature of the cold object. The internal energy decreases for the hot object, increases for the cold object. The amount of internal energy that turned into heat is called enthalpy. Enthalpy is one driving force that determines whether a chemical reaction occurs. The other driving force is entropy. Entropy refers to the dispersal of energy. Another way to look at entropy is the amount of disorder in a system. Now consider these two statements. The first one explains why rocks roll naturally downhill, not uphill. The second one explains why you have to expend energy to clean your messy room. Once you clean your room, it gets messy naturally. This picture is related to entropy and the dispersal of energy. Now, every chemical reaction involves energy. In an exothermic reaction, heat is released, for example, a candle burning. In an endothermic reaction, heat is absorbed, for example, a cold pack. Where is the heat going or coming from? The surroundings. We can quantify how much energy is involved in the chemical reaction by calculating the change in enthalpy, delta H. We will apply Hess's law to calculate delta H for a reaction. To use Hess's law, the first thing we need is a balanced chemical equation. N refers to the coefficient for each reactant and product. We will look up delta H formation of each reactant and product in a table. This symbol refers to the sum. So we have to take the sum of N times the delta H formation of products and subtract it from N times delta H formation with the reactants. A positive delta H reaction means the reaction is endothermic. A negative delta H reaction means it's exothermic. To use Hess's law, we said we have to look up the delta H formation of each reactant and product. Formation refers to a formation reaction. In a formation reaction, the reactants are the elements in the standard state, and the products are the compound formed from the elements. By definition, delta H of formation of an element in a standard state equals 0. Here are two other terms we want to look at. So stable means low energy, and unstable means high energy. Usually compounds are lower in energy or more stable than the elements it came from. This means that delta H formation of a compound is usually less than 0 or negative. Let's look at a formation reaction and compare the energy or stability of the elements to the compound. So stop the video, look up the delta H formation of these substances, and then figure out these two questions. And the answers are, remember, delta H of formation of elements in their standard state equals 0. Delta H of formation of water in its liquid state is minus 285 kilojoules per mole. This number tells that liquid water is more stable or lower in energy than the hydrogen and oxygen it came from. Next, compare delta H formation of H2O gas to H2O liquid. The numbers tell us that H2O liquid is more stable or lower in energy than H2O gas. So the substance with the most or highest energy is, and the most stable substance is, An energy diagram looks like. This energy diagram shows that H2 and O2 are highest energy or unstable, and H2O liquid is lowest energy or the most stable. Now you're ready to calculate delta H for this reaction. Stop the video and apply Hess's law. And the answer is, here's how we got that answer. First, balance the chemical equation. Next, look up delta H formation of each reactant and product. Then plug in the numbers in the Hess's law equation. The math tells us minus 570 kilojoules. This means 570 kilojoules of energy is released. This amount of energy is released when 2 moles of water forms. Stop the video and fill in this blank. And the answer is, this energy diagram shows that when H2O liquid forms from H2 and O2, this is an exothermic reaction which releases 285 kilojoules of energy. In an earlier video, we said that metals lose electrons to form cations. This is an energy diagram of a few metals and metal ions. Stop the video and answer this question. The answer is iron 2+ is lower in energy or more stable than iron. Iron prefers to be an ion, that's why iron metal loses electrons to form that ion. On the other hand, copper metal is more stable than copper ion. So copper prefers to be a metal and will not rust to form its ion.